All right, let's dive in. Today, we're going to pull back the curtain on one of the most important documents in the entire industrial world, ASME B31.3. Now, I know, it sounds super technical, but this is literally the safety code that keeps our world from falling apart. We're going to break down its core ideas, so let's get right to it. You know, every time you see one of those massive industrial plants, what you're really looking at is a huge, complex web of pipes. The B31.3 code is the rulebook, the instruction manual that makes sure those pipes don't fail. It's really the DNA of safe design. So how does it do that? How does it transform a simple tube of steel into a structure that can handle insane pressures and temperatures for decades on end? So here's our game plan. We're going to walk through this the same way a designer would. We'll start with the most important question of all. Who's even qualified to do this work? From there, we'll get into the gritty details of the design conditions, understand the incredible forces and stresses involved, look at the materials themselves, and then finally, see how it all comes together to create a safe design. First things first. The code is crystal clear about this. You can't just have anybody designing these critical systems. It all starts with the right person, someone with proven experience, who's in charge right from the get-go. And this is a really big deal. The code doesn't just say, oh, you need an engineer. No, it sets a very, very high bar for what it means to be competent and experienced because, well, the stakes are enormous. So what's the magic formula? What does it actually take to be considered a qualified designer? If you look at section 301.1 of the code, it lays out 4 different ways you can qualify. And you'll notice a theme here, right? It's always a serious combination of formal education and, critically, years and years of hands-on, relevant experience. Whether you've got a degree plus 5 years or a solid 15 years in the trenches, the code demands that you've proven you know what you're doing.
Okay, so we've got our expert. What's job number 1? Well, they've got to understand the world this piping system is going to live in. You just can't design something safe if you don't know exactly what it's going to be up against every single day.
And the designer has to juggle a whole bunch of things at once. It's not just about the pressure and temperature inside the pipe. You got to think about the environment outside. Those dynamic forces, like a sudden fluid surge, the sheer weight of the pipe plus everything in it, and of course the constant push and pull as things heat up and cool down. Every single one of these is a potential weak spot if you don't get the math right. Now, what's really fascinating about this slide is what it tells us about the code's whole philosophy. This quote right here shows that the code is built to be conservative. It forces the designer to plan for the worst-case scenario always. If a pipe is going to see a bunch of different temperatures, you have to design it for the one single temperature that requires the thickest, strongest material. No exceptions.
Okay, we know the environment. Now comes the real fun, the physics. This is where we get into the engineering challenge of figuring out and managing all the physical forces that are actively trying to tear the pipe apart.
Before we go any further, we have to get our heads around this one key concept: allowable stress. Every material has a breaking point, right? Well, the code takes that breaking point, slaps a big safety factor on it, and gives us this value S. You can think of it as a speed limit for stress that your design is absolutely not allowed to exceed. It's the foundation of everything.
And this slide just lays it all out, doesn't it? It's a constant battle. The pipe is under assault from every direction. You've got pressure trying to blow it up from the inside. You've got dead loads, just the immovable weight of the pipe itself. Then you've got live loads, like snow piling up. And on top of all that, you've got vibrations, wind, even earthquakes. The designer's job is to add up the stress from all of these things combined.
Let's talk about those cyclic effects. You know how if you bend a paperclip back and forth, it doesn't break the first time, but if you keep doing it, it eventually just snaps? That's metal fatigue, and that's exactly what this graph is showing us. The more stress cycles a pipe goes through, the weaker it gets. The code makes designers account for this slow, gradual weakening over the entire life of the plant. So we know the stress limit, we know the speed limit, but here's the catch. How do we really know that the material we're using is as strong as the textbook says it is? Well, the code is, let's just say, a little bit skeptical. It assumes that nothing is perfect.
And that is where these things called quality factors come into play. You can think of them as a penalty, basically. It's a factor that reduces the material's strength on paper to account for hidden flaws that might have come from the manufacturing process. It's the code's way of building in a safety buffer for the real world. The 2 big ones you'll run into are the casting quality factor, EJ, for parts like valves that are made by pouring molten metal into a mold, and the weld joint quality factor, EJ, which is all about the seams that hold the pipes together. The code basically says, hey, a weld or a casting is a potential weak spot.
so we need to be extra careful with it.
But here's the cool part. You can earn that penalty back. This table shows it perfectly. If you only do a basic visual inspection, the code says, nope, we're only going to let you count that as 80% as strong as a perfect piece. But if you bring out the big guns, X-rays and ultrasonic tests, and prove there are no hidden flaws, you get to use a factor of 1.0. You get full credit for the material's strength.
Okay, deep breath. We have our qualified designer. We've defined the harsh conditions. We've calculated all the nasty forces trying to break everything. And we've even accounted for imperfect materials. Now, we bring it all home for the final, most important check.
And this is it. Seriously, if you remember only one thing, this is it. This is the heart and soul of the entire code. The total calculated stress on any part of that pipe, from everything we just talked about, must be less than or equal to its allowable stress, that S value. If the calculated stress is lower, the design is safe. If it's higher, it's back to the drawing board. End of story.
This final quote just wraps it all up perfectly, doesn't it? It's the code's non-negotiable command to be conservative, to imagine the worst possible day that pipe will ever have, and to build in a margin of safety at every single step of the way. This is why our industrial world is as safe as it is. And that brings us to the final thought. As we push materials to new limits, as we build bigger and more complex plants, the challenge of keeping things safe never really ends. Codes like B31.3 aren't set in stone. They're constantly updated with new science and lessons learned from past failures. So the real question is, how will this vital process of constant improvement keep up with the demands of the future?